Hi everybody. Thanks for that lovely introduction. I'm really fortunate to be able to give this presentation. I represent a large team of people who have all worked on this project. This sort of project has its origins back in the Natural Disaster Insurance Review of 2011. I'm sure most of you can remember the big floods we had in 2010-11 up and down the east coast of Australia. And there was a little bit of controversy in terms of what constituted a flood. So the decision was made by the government to come up with a single point of reference in terms of flood information. Hence the National Flood Risk Information Project was born. And so this talk is to describe how satellite imagery is analysed to inform that process. So what I'm going to give you is a very quick rundown on satellite imagery and Earth observation, and then we'll go a little bit more into the specifics of how we map floods using satellite imagery. So in February last year I was lucky enough to go across to the US and watch this live, which was a lot of fun. And it doesn't sound like we've got sound on the videos, but that's all right. So basically what you'd be hearing is the classic countdown. And you know, we've all played games as kids doing countdowns for rocket, but I tell you what, when you hear one real and live, the level of adrenaline is something completely different. And I was used to watching the launches of things like space shuttles where you get big plumes of smoke. So a liquid fuel rocket like this one almost looks like an upside down Bunsen burner, very, very clean. Fascinating thing was when I was watching, I didn't realise that it was going to start tilting about now as it gets ready to be inserted into orbit. So as I was watching it gently starting to tilt over, I'm like, uh-oh, she's going to keel over and fall out of the sky. Thankfully, it didn't. So this is the Landsat 8 satellite, which is the latest in a series of satellites that's been launched by the US government. And so the satellite basically is up here, safely ensconced in the nose cone. And at this point it's sort of, under an amazing amount of pressure as it's being pushed up out of the Earth's gravity up towards its eventual orbit around the Earth. And in a second it'll go, the voiceover says it goes into beyond the speed of sound, and a big plume of white vapour comes out behind it, which looks pretty cool. There it goes. The flame starts to widen out as the air at that altitude starts to thin out. And so that's the satellite being launched up into orbit. And I've got one more YouTube video for you, which is this one here, which is really a nice summary of satellite imagery itself. So what happens once you've actually got so a satellite comes over, acquires a strip of imagery, and the video stops. That wasn't supposed to happen. Right. Come on. Come on, don't do this to me now. Alright, seeing as that's not going to play ball, the underlying idea is that you get a swath of satellite imagery that comes down and you get an individual scene that represents a particular chunk of imagery. So, using imagery to detect change over time. That's yours truly, quite some time ago. A little bit later on, you can see there's been a fair bit of change in the imagery. And then, more recently, you can see there's change again. It shows you a couple of interesting things. First thing is, if you wanted to pull out consistent features out of that imagery, let's say my eyes for example, you'd have to identify common features within those images, and then you'd have to account for the view angle. So here, my head's facing that way, here the head's facing that way, here I'm looking straight ahead. So you've got to account for the view angle as the imagery as well. Then of course you've got changing sensor technology. So you've got a black and white camera, You've got a colour film camera, and finally digital photography. Now obviously I've scanned them all in, so they're all now digital images, and it's a lot more easy to compare digital images than it is to compare film or hard copy images. And you can do things like automated feature recognition. Who here's been through customs recently? Anybody seen those new fancy scanners where you don't actually have to walk up to someone, they just scan your face? Didn't work for you? It was probably the beard. So fascinating thing, and likewise, if you've been using Facebook and it says, oh, would you like to tag so-and-so? Facebook is running facial recognition that can do automatic feature recognition and using biometrics to try and figure out who you are and what you're supposed to look like, which is amazing to see that the technology in terms of automatic feature recognition has come as far as it has. So here we're using automatic feature recognition to do something slightly different. We're looking for water rather than looking for faces. Now who would like to have a crack at what in that image represents water? Come on, someone have a go. The light blue? That's correct. These blue features up over here are the lakes, and this is the sunny little town of Kerrang in Victoria. Now for those of you that have been to swimming pools and looked at rivers around Australia, is water always the same colour? Does water always look the same? It doesn't, does it? You can have brown muddy water, you can have deep clear water, you can have lovely blue crystalline water. So the colours change. And satellites measure colours, or the way that the sunlight is reflected off the Earth, and so it reflects the sunlight that we see, and it also captures wavelengths of light that we don't, which was explained really nicely in that other video that didn't play, but leaving that aside for the minute. So there's the sunny little town of Kerrang, satellite image acquired at a different time. You can see that there's a fairly large amount of flood water, different colour to the other water. This is a black water event, so there's a lot of carbon stirred up in the water. And you can see a system of levees here is actually keeping the town of Kerrang nice and dry, whilst the rest of the landscape is underwater. Which is really neat. So all you need to be able to do now is automate the extraction of where that water is, stack it up over time, off you go. Sounds easy. So, coming back to the wavelengths of light that we can see. So if you were strapped to the bottom of a satellite, 750 kilometres up, whizzing across the Earth's surface, this is roughly what you would see. You'd see, as it turns out, this is flood water, clouds, cloud shadow. Notice that cloud shadows are black, we'll come back to that later. And you can see what could be flood water because it looks the same sort of colour as this, but as it turns out, if you look in different wavelengths of light, that's just bare soil that happens to have exactly the same colour as the flood water because the flood water washed across the bare soil, and so it's all much the same colour. If you look down here, you can see that the flood water is very, very different to this area up here. So this is your bare soil, there's your flood water, mixing together with another sort of flood water as it's rocketing down the river down there. So you've got to start to have automatic recognition that deals with the fact that water changes colour and appears differently at different parts of wavelengths of light. Anybody got any questions at this point? Nope. Good. All right, another animation. Hopefully this one will work. Here we go. So this is a satellite called MODIS. MODIS comes across twice a day, and then you can composite that imagery up to get rid of all the cloud shadow. And so this is, you can see time ticking along up there, and this is the floods that occurred in 2010 and 11. And you can see these flood waters pulsing down here in your dark blue colours. And you'll see another nice big pulse come down in a second, so we just zoomed in a little bit. You can see those nice, those flood waters pulsing down through the landscape. And so this just gives you the feel for, and there's Brisbane up over here, in Brisbane, Toowoomba, St George. You can see St George is getting a nice little bucketing every now and then. And those of you that would have watched the news would have seen that St George, did get floods during that period of time. And so by looking at this sort of imagery over time, you can start to build up a picture of where the floods get to and how frequently they get there. You really are going to be a pain in the neck today, aren't you? So, different types of satellites give you different types of information. You've got MODIS that we just saw then, comes across twice a day, but you've got a 250 metre pixel. So the smallest thing it can resolve on the ground is 250 metres by 250 metres. So this entire building would fit within 1 pixel, more or less. Then there's a different satellite, like one which is called watched getting launched, which it comes across once every 8 days, but it has a 25 metre pixel and has been acquired since 1986. So in terms of the imagery we've just been looking at, that's Landsat, that's MODIS. So there's quite a clear difference in image resolution, and the observant ones out there will say, hang on a second, the clouds have moved, and they have. This one's acquired on the 21st, that was acquired on the 20th of January. So the clouds have moved, but you can see that the floodwater is much the same sort of extent. The really important thing here is that this one, the entire archive of Australia is in the hundreds of gigabytes of data. Now here you've got hundreds of terabytes of data. Now hundreds of terabytes of data suddenly gives you a much, much bigger series of problems. To use Stuart's favourite analogy, hundreds of terabytes of data. When you get up to 1,000 terabytes of data, that's called a petabyte. If you were to put a petabyte of data onto old school CDs, the stack of CDs would be as tall as Mount Everest. So clearly that's a lot of data to contend with. And in terms of looking for floodwater in that kind of amount of data, you're looking at probably in the order of 21 trillion records. So if you imagine you've got to sort 21 trillion marbles into various different buckets, looking for different colours of marble, which is essentially the task at hand here. You're basically sorting marbles into buckets to try and figure out which ones are wet, which ones aren't. You need a really big computer to be able to allow you to sort through trillions of records. So, a couple of tricks you need to do first. First is to take the scenes as they're acquired by Landsat and then stack them up over time so that you can compare things easily through time. And what that looks like is you end up with a grid of data that can be then broken right down into individual slices. And so by the time you get down to here, this is where you've got your individual marble that you've then got to try and classify. So you end up with a big stack of imagery, stacked through time, one particular observation in time, one particular pixel, and then the task of classifying it. So, needless to say, enter the supercomputer. This is the Region supercomputer located over at the National Computing Infrastructure. 57,000 cores, 160 terabytes of RAM, and 10 petabytes of hard disk. And it's used by a range of different agencies. And it was this computer that allows us to do the kind of task of sorting 21 trillion pixels in 6 to 7 hours rather than 4 years. Because if you were to do it on a standard desktop, you'd be looking at around 4 years worth of analysis as distinct from 6 hours worth of analysis. So clearly, if you need to improve algorithms and work on things and find out where it works and where it doesn't, if it's going to take you 4 years every time you run the code, it's just not going to happen. So this has been transformational in terms of changing our capacity to do this kind of analysis. So basically there's a bunch of steps. First step is to calibrate the imagery so you can compare change through time. If you think about the original photos of me when I was a baby through to now, you basically got to try and bring them all into a standard set so that they can be compared over time. So then you've got to go through and automatically weed out all the cloud and cloud shadow, and that's a tough job I can assure you. And then you've got to find a way of automatically detecting the water based on the way it reflects light, notwithstanding the fact that water gets to be different colours and can sometimes look like other things in the landscape like shadow. So lots of testing was required to work through 15 years of data, all times of the year, all climatic conditions and all terrain types. So another little animation. So this is just an animation showing you the way the imagery gets acquired across Australia. You then dice it up into nice even tiles, and this gives you a feel for the way those tiles can be stacked up over time. And you'll notice that you're not seeing every bit of that tile every time. And so you get stacks of imagery all across Australia. And then by looking at that through time, you can actually start to understand where the floods are. And then looking at that in a little bit more detail, we're about to zoom into the Menindee Lakes in New South Wales to give you a feel for exactly how we get to the map that we're looking at the moment. So here you've got your imagery stacked over time, and you can actually see how the extent of water through there is shifting around. And now you're seeing the water detection algorithm. So that's actually showing you just how it's picking out the pixels that have been identified as water. And that tracks over time, and then you can summarise that based on how frequently water has been observed. So then we've got quality control results. So we're more confident in terms of the amount of water in known water bodies, on floodplains, and in areas where there's been lots and lots of satellite observations. And clearly we're less confident about water in urban areas because the pixels get about the same size as houses and rivers, so it gets kind of tricky to make out the water in urban areas and in areas where there's high slope. And we include these measures to inform users about how confident we are in the results of the analysis. So this is what that result looks like for the Menindee Lakes. And so you can see you've got everything from water detected in 1% of the observations right through to water always detected. So the advantages of this sort of analysis is you get a detailed summary of observed water over 15 years, which gives us new insight into the way that water moves through the landscape, which is especially valuable in places where there's sparse stream gauging networks. And it's less likely to capture fast-moving floodwaters in steep catchments. And infrequent observations may miss the flood peak. So if you've got a very fast-moving flood peak, satellite comes across, doesn't observe it, you won't capture it. And likewise, it doesn't capture the fine detail in urban areas. So this isn't necessarily the right information tool in places like Brisbane where the floodwaters get quite complex and interspersed with the urban areas. And this has all been publicly released. So this is the part of the GA webpage. So this is the Australian Flood Risk Information Portal. And if you were to come to here and then click on the water observations from space layer, you'd get to come through to this link. And hopefully this will work. And so this is the result of analysing 15 years of data on a supercomputer, and it shows you the extent of surface water and how frequently surface water was observed across Australia. So seeing as we're down here in Canberra, we'll go with somewhere that we're all fairly familiar with. And somewhat reassuringly, you can see that Lake Burley Griffin has been observed 296 times and is basically been observed as water that entire time. Probably a few clouds that have managed to skip through there. But if we come up and have a look at Lake George, you can see a fairly different picture. So the very edges of Lake George have been observed as water 10% of the time because, ebbs and flows. But down in the deep parts of Lake George, water gets observed around 36% of the time. But that reflects the fact that all of Lake George dries out during the middle of the drought. So you can zoom around and have a look at, this is really interesting, this is all the flood irrigation that happens in and around Griffith and Wagga. So if the satellite comes over when they're doing flood irrigation, you can actually see where the surface water gets to. And that area that we were looking at before in terms of Kerrang. So you can now see the town of Kerrang and the other water bodies around it, and you can see how the levees are actually keeping the town of Kerrang dry throughout the whole time. But you can also see that there are other farms out and around the place that are subject to flooding on a reasonably regular basis. So this information also has value above and beyond just flood risk information. If you were going to go for a drive across the central deserts of Australia, you'd probably eventually end up going through this neck of the woods. And it's really interesting because you can actually see that there's a highway coming down through here, and that highway goes in through an area that gets flooded fairly frequently. So that road gets cut off on a reasonably regular basis. And if you zoom in, you can even see the levee associated with that road causing a change in inundation frequency. So you can see they're running that highway along the top of a sand dune, then they have to go across the floodplain through here, and then it pops back out again. But if you understand which seasons that flooding is likely to occur, then you can plan your trips accordingly and make sure you don't wind up getting stuck at one side of that floodplain for a couple of weeks while the floodwaters drain through. Now, is there anybody here from out of town? Not from Canberra?
Sutton.
Sutton. We can go and have a look in Sutton. I don't think there's not a lot of these nice big slow-moving floodwaters out around Sutton, which probably isn't a bad thing as far as you're concerned. But we can duck in there and have a look. So I think most of the interesting activities around this part of the world, you can get out of some fairly small farm dams in and around Sutton, but there's not a lot of big extensive floodwater. So the most interesting feature in and around Sutton probably is already Lake George, which we already had a look at.
Can you tell how deep the water is?
How deep? Not exactly, not without additional information. You can tell how frequently it goes underwater, but you need something called a digital elevation model to tell you how deep that water is. So you can start to identify which areas are of the same height because they're inundated at the same time, but you need additional information to tell actually how deep the water is. All right. Thanks very much for listening.